Hello, everybody. Give me a thumbs up if you can hear me. We are here today for another session of community conversations for our Technomatics virtual user group, and we are talking about value stream mapping today. Our speaker for today is Robert Forstner. He has been working for 15 years as Simplan AG, which some of you know. One of our community catalysts, Alex, also works at Simplan. Robert has served as in a consulting role since 2018, and his work focuses on the simulation of intralogistics production systems and value streams using Technomatics plant simulation, including the use of a value stream mapping library. He also serves as SimVSM contact for Simplan. He supports activities related to development, rollouts, and maintenance with plant simulation used as the backend. So he'll also talk a little bit about that today. Our agenda, the big steps he's going to go through are building value stream models, model material and information flows, analyzing processes, and distributing the models to a shop floor using, in this instance, SimVSM. So again, we'll follow that with a live Q&A, but if you think of something in the moment, feel free to put it in the chat and we'll get to all of those as well. That is it for my introduction. So Robert, feel free to take the screen.
All right, so thanks, Taryn, for the introduction, and welcome everyone from my side as well. So today it will be regarding value stream mapping and value stream mapping library within plant simulation as a, let's say, more specific area or specific topic rather than the, let's say, other sessions. For example, with Alex Dillig or Steffen Bangshoff, which were more plant simulation basic objects with basic modeling and simulation. Value stream mapping is more from the lean community, and for this in plant simulation there is a specific library to support that with a certain set of toolbox, icons, etc. Just for a short introduction to value stream, here are 4 examples display how value stream is done traditionally in a traditional way. Normally with paper and pencil on a brown paper, you draw your value streams up with standardized icons, meaning you can have icons for example, processing, for inventories, for transport, and also for information or order flow in a pretty simple but standardized way, or at least kind of standardized with each standard and own companies. But the idea is to have a simple way to describe a shop floor and the mechanics of a shop floor, how material is flowing, but also based on what order and what information material is flowing. And then with this very simple documentation, you would have an average analysis, so to speak, of demand, of customer demand, also of cycle times of stations, also of inventories and transports in between. And you basically learn to see, so that's a kind of also model of lean or lean management in this instance, learning how your shop floor is working in a very simplified way of description and modeling. And for that, basically, there was a VSM library implemented. So as a short introduction to what's the library and how is it available, it's basically a dedicated library within plant simulation, also distributed with plant simulation, and it was developed by Siemens, also I think based on a research project, and also due to a research project with Simplan AG, there was a further exchange, and afterwards it was decided that Simplan got the opportunity to further develop and also take care of maintenance of the library to further push features or also architecture features I can show later, which are also coming from research. One special point for integration in plant simulation in the library itself, it's included in the regular plant simulation distribution. So if you install plant simulation, this library comes with it. With checking the class library manager, you can activate your library right there. And it's distributed also with every patch. There might be also patch from plant simulation, there might be a patch for the value stream library. And one special note is it was already a special license under Siemens and it stayed that way. So in contrary to earlier sessions where the focus was on use objects which can be also used with foundation license or not very specific licenses which cost additionally with plant simulation, this is not the case today. So for the library you would need an additional license, and also as a short note for the software afterwards, there's also a first free version, but the additional company software architecture also is additional cost to plant simulation as a short note beforehand. All right. So also a few characteristics for the library. So this is a fully self-contained library. So all what you would need to model is within the library, and you can define the library through dialogues or only through dialogues and the configurable elements, which are the object itself. So often it is asked, can you combine it with plant simulation basic objects? That is also not the case. So due to internal logics, for example, an order is coming into a station, which is withdrawing parts from an inventory. So there's internal attributes, there's internal methods which are calling each other, and that's why a simple combination with basic objects is not possible, at least for now. We can't promise anything, but we heard it before that might be a good extension to keep in mind. And we are always thankful for input or feature requests. Yeah. And then basically we have predefined objects. We will see it in the toolbox for processing, storage, transport, and also important the order management. So how are orders flowing through the system? Maybe one short note also afterwards is there's an internal heavy usage of SQLite and memory databases. So if you save run models, so run models maybe after 5 days, and you reopen it, you would need to restart your simulation because a memory database is not persistent on a model. All right, maybe also a few comparisons. What is a key characteristics with based on value stream simulation in comparison to a basic object simulation, maybe something similar to what we've seen last session with Steffen Bangshoff, where you have a simple push line maybe on the left. So you have a material flow definition from a source to drain. For value stream, it would be from a supplier to a customer. Might it be internal or also external? And first, you would say, okay, I define here a processing time for a station or maybe a buffer capacity. That's pretty much the same for value stream. It's just might be different naming. So instead of proc time, it's a cycle time. So the difference between two part exits from a station. But you would also have, for example, failure rates or a mean time to repair, some prepared exit strategies that might be quite the same with a push and material flow indication. But what's the main difference is in a basic plant simulation model, you have the opportunity to integrate a method into your station and there code your own logics and your own behavior. And that's predefined with the value stream library, where material flow is based on orders and based on how these orders are pushed to the station. So basically, the main origin of every material movement, or the most of the origin of the material movement, are orders which are defined in the customer. So that's the main starting point from a static value stream analysis and also for the simulation. So this customer has a defined demand per hour, per day, or a certain interval. And then this customer is ordering products, which is then forwarded to a production control, and this is then forwarded to certain stations. So orders are transitioning into local order queues, and these order queues are then executed. And based on these orders, material flow is induced. For example, also how much parts a supplier has to produce. So can be information flow push or even a supermarket pull in different instances, but that might be an additional focus of that lean management area where you say, okay, you have a more aggregated view on a shop floor with standardized icons for supplier, customer, processes, and inventories. And based on that, you would have material flow and also an order flow to trigger material flow in the stations themselves. So just as a short introduction, what might be a bigger difference towards basic objects besides maybe the main one that objects are locked, fixed, and you can only combine them within. Another important point why simulation might make sense in also a value stream analysis is normally value stream is just interpreting a product family, meaning you collect 70-80% of products going over the same sequence of machines, and then this product family is assigned to every station with a cycle time which is an average. Could be a weighted average or just an average based on parts. And since we are all known to plant simulation and the more detail-driven approach of simulation, this allows us to do a value stream analysis which is product assigned. So you could define, for example, a product for a customer and then product transitions in between. That might not be news or something special to your plant simulation expert, but for value stream, this might be a new addition also to have not only product transitions, but also parallel product definitions. So you say you not only define one product at a customer, but also several products with different demands maybe, or with different cycle times at a certain station. So that would be basically a more, let's say, realistic approach to different products instead of maybe just an average view on a certain value stream. All right. And with that, I'll change to plant simulation to show the certain workflow. Just a second. All right. So, all right. Good. So this is the latest plant simulation version with Patch. Just a note for you, since value stream mapping is not so much in animation based focus, so I can show you that it's working in 2D and 3D. This right now would be 2D, but it's in 3D working as well. It looks just the same if you go to the planning view. To activate the plant simulation value stream library, you just go to the home, to the class library manager, where you can activate certain basic objects and additional libraries. And when, or if you go to libraries, there is standard libraries, and then there's a licensed with value stream mapping, which you can activate. And with the note earlier, for that, there is the additional license necessary. With this activated, we then basically have an object right here with the before mentioned standardized icons with behavior behind it as plant simulation objects for different purposes. For example, for production planning as a central unit in the middle, you have a supplier customer as a basically source or drain, different process elements for different behavior, which might also be a new approach for historical lean users, where a process is just a box drawn on a brown paper. And then also storage, inventories, and transport, etc. Also available here on top on the toolbox. Yeah, and if we now then go to the objects, we can basically start with the first basic structure. So the first element needed would be a production control. This is also checked. So if this is not available and you insert something else, this is also automatically inserted. So this object holds central administration, error handling, internal product administration, many different elements, and that's why this is also a one with a network object, so it's only allowed to have one, but you need at least also one. All right, good. So starting, you can start with the supplier or the customer, depending what lean theory you're approaching. Normally, it's easier for humans to model from left to right, but it's also quite common to just go upstream from the customer. You can then use, for example, two processes which have the icons similar to Lean objects and Lean literature for the value stream map. And then, for example, you have here two inventories. So these are unlimited inventories as buffers where you store parts, and these inventories would rely on that they are replenished based on certain order flow. Creating a first material flow would then need the connectors here on the top left. So there are different connectors for different purposes to indicate also the difference between the material flow, for example, and also the information flow. So starting from the supplier, you would connect it the same as basic objects, also holding control. You would be able to maintain this mode. Just connecting your material flow with the certain connector. We can also do maybe just renaming with inbound, then processing, right, with basically source and a drain for a customer, but the difference is this would also be order driven. All right, so besides material flow, we would then also have information flow. So how is the customer basically defining a demand and forwarding its demand? It's forwarding the orders. It could also be, in a special case, maybe directly to a supermarket at the end, but now in a regular case, it's forwarded to a production control. So for example, 60 parts per hour, what we would define. These orders are then forwarded to a process, and customer orders are calculated automatically with the material requirements planning algorithm to the next control station. And from here, it would also be automatically calculated upstream to the next connected station right here, and would say, I also have to produce here parts according to a certain customer order. And the last connection would be here necessary between PPS and the supplier. That would be a special connection, because this indicates calculation for orders for the supplier, how much part the supplier should provide, depending on the demand of the customer. So customer has, for example, 2,000 parts per day or 1,000 parts per day, then depending on the horizon and the parameter, the supplier should provide all necessary parts for that as a integrated source based on orders. All right. So with this basic structure, we will basically have our first value stream, and then what we would do is add the products we've seen earlier. So this is now an empty structure. Parameter for the products would be inserted by dialogues with the objects, which are then otherwise fixed. So what we now need to assign our products and attributes for these products within this value stream. So for example, we have here a customer demand. And this would then be, for example, besides general order sequence, so we have a demand on a customer cycle per individual product, we switch to the tab product, and we would add here a new product which hasn't been created. For example, one final product. For easy calculation, this would be 60 per hour. So time format the same as in plant basic objects, seconds, minutes, hours, and range of variation would be you can have a random calculation for each order. So for example, 65 or 55 to have a variance in your orders there as well. So then we have assigned here basically a product which is a final product. And this now is produced within a station right here. So in processing, we also open up the dialog quite similar, and the mechanisms for the product assignment is always the same. So you have a table for different products, since we can assign different products to each station. So customer can order different products, station can produce also different products. So for here, we would add the same product. So here's a pre-selection of this product available. Can for now maybe also do this here the same, and then we would just say, okay, this is just an easy example to have this here integrated. So a final product would here be produced. To also integrate here a product transition, we can say, okay, here is a different product included. So this station right here would produce a different product, which is raw product just entered. Yes, like this, and this has, for example, a quicker cycle time in comparison. So based on this, there would now be a product transition, and for that, this can also be defined within the station, where you can say, okay, I have here a product which is going out, and another product which is coming in, which is the base product. So product coming in, transitioning to another product with a certain number of consumed products, but this is now the product before, so we would have a product in transition. So to have this defined there, we would have here basically a transition from raw product to final product, something like this, in the quantity of 1. And with that, we are almost finished. We just need to adjust the inventories to say, okay, the product before is also being stored right here, and also the product before is stored right here. What you would here also see for the inventories, product-wise, there is not so much to define. One would be initial stock, so you could start a simulation, for example, with pre-filled inventories to maybe skip the first balancing phase where you have a ramp up of your simulation. All right, so we have a product right here, and then we would assign the product until the supplier, where we also just need to define the product, which would here now be the same. So it's always the same mechanism. You have a product table, you open it up, you can select a predefined table, a predefined product within this table. You have a packaging size. That would be the number of products put into one carrier, transported to the system. Could also be a mechanism later in the objects there as well to combine products into a carrier and then use this as a transportation unit for the next transportation time. All right, so with that, we always made sure that the product transitions are correct. So we have assigned products, we have assigned attributes, etc. And for this, and to have this correct, the library has also some tools available, and one of them is, for example, the check tool, which now can be executed and say, okay, there is no modeling errors found. So a modeling error could be, for example, that inventory right here doesn't have any product, so we could delete that, execute that again, and then there would be a report that supplier and a base product supplier process or supplier is not finding the product in any successors, vice versa for this station right here. So there is a whole list of check routines to support a user, also to give localized feedback if some things are missing, and these checks are also consistently updated for new constellations which might have not been thought of, or just new feature constellations there as well. All right. Good. So with that, we have a first value stream and can basically already run a simulation. Would be the same for with just adjusting the event controller would be the same for value stream as for basic objects. Just put in here an end time so it doesn't take too long. If we run this, we basically would see, okay, from an animation point, it's not so much exciting. So you basically see parts running through the system. Once a part is on a process, there is an animation if it's worked on, and also it would look like the same in 3D. So if we open this up, you'd have the set axis for inventory, but if you go to the planning view, that would be look exactly the same here in 3D as well. All right, so just to explain what the order mechanism is now basically doing, or what certain mechanisms are there available. You can see that you have certain products with orders there. So, for example, you have here a certain order table, local order table for this process, and this has to produce 60 orders, 60 parts in one order for a customer order, and this can also be viewed in the customer there as well. So the customer has in its dialog there are also statistics to check this. And one would be you have just a simple order protocol. So what was ordered and when was it finished? Just a second. Oh, this is too long. Yeah. Just a second. Right. Yeah. Okay, so under statistics, you have order protocol, and then this order has now received. It should be quite simple with the time or with the static calculation. Each order has a certain number ordered at. So every hour, this basically is an entry. Customer is ordering 60 parts. The 60 parts are distributed to this station, and to this station you have a local order which is then activated once this inventory holds enough parts for the whole order, and then the order is activated and then basically pushed forward to the successor. So with additional statistics, this behavior can exactly also be looked at. For example, if you have here settings for a stock plotter for the first inventory, you would see at the beginning of the day, this is exactly 1440. This is the number of minutes per day replenished, and over the time of the day, this is then withdrawn, and again at the beginning of the next day this is replenished, etc. So this is at the beginning the exact number what the supplier has to provide for the station or for the whole system based on customer demand and also based on a disposition interval. So the production control is calculating how much parts it has to provide within the next disposition interval, and this is then an order for the supplier. So if we extend this to 3 days, for example, it would just be a higher initial stock for the 3 days, should be 4,320 something. To survive 3 days of inventory, and that would mean it's not replenished within 1 day. The same would be here for this inventory. You have here also the same setting to plot the current stock values, and this would behave as such that you fill this inventory up till 60 because that's the number the order is coming in from the customer, and then it's withdrawn. So basically, you replenish a certain inventory, you withdraw it, replenish it, withdraw it, and this goes up to 60 because once 60 are available, it's taking out parts from here. Additionally to such inventory statistics, there's, for example, also statistics for processes and also an overview statistic. So an overview statistic would be this tool right here. So this is called utilization and stock, which is a combined statistic view of process states over time in percentage. It's the same for plant simulation basic processes, and also it's including stock at the current time in a relation to the max of stock. So the stock is drawn to the negative, and the utilization of processes are aligned horizontally from left to right in X and Y axis, or sorted by X and Y. And there you would see also always a big indicator how the processes are utilized, or what might be a certain a certain factor for optimization. Is a process waiting on parts? Is a process blocked? How is a process behaving depending on maybe setup times? This is quite similar to the basic objects there as well. One enhanced difference is here, for example, the integrated different status for waiting. So if a plant simulation basic process is waiting, it's basically waiting for parts. It's available to produce, it's waiting for parts, and it's planned in a planned shift calendar time. And right here you would see the effect for the value stream, also the combination between the material flow and also the information flow. So the first station right here is now utilized almost half of its time, and that's although there is a lot of stock in the inventory at the beginning. So it's a lot of stock available, and this stock hasn't withdrawn, although the process would be fast enough. But it's waiting. It's basically finished after a half hour, but it's waiting until with the end of the next hour, the next order is coming in, and it restarts to produce. So if this would be a regular push environment, this process would just keep producing. But here it is waiting for the next order, and it could be this is now just for demonstration purposes, that you have a product and this is ordering every hour. And this could also be that this is every day, or it's based on a certain list where you can put in products and a certain demand and a certain time for it. So it's just based on what's coming in as order. This induces material flow. Induces material flow through the system and also through the stations. This effect right here. So as maybe an additional statistics, also quite interesting, is there are, besides basic static statistics, also similar to plant simulation basic process objects, there is advanced statistics based on intervals. So for example, you have an integrated interval counter, so how many parts have been produced per hour. And this is now quite static, not very exciting, but it's every hour it's the same. So every hour you have 60 parts, for example. Or you have also interval statistics for this process, and there you would see the exact behavior. So utilization the same as before, but this is now in x-axis is split up between hours. So you would see in each hour it works half the hour and waits half the hour for an additional order to come in to already consume some of the plenty available parts beforehand. And these are then also available throughout the stations, different station objects, to have these interval counters additional to total counters. So not only count how much parts have been produced after a day, but also how the intervals are structured there itself. All right, good. So after maybe a first simple introduction to these elements, I can also show you an additional tool. So that would be also a confirmation if products are correctly designed. You would have here also visualization of your product structure. So this is not quite exciting with just 2 products and a transition quantity of 1. So 1 raw product is going to a final product. But if you have several assemblies, this can be quite interesting and also quite complex for further, let's say, clearance of visualization, a simple understanding of a value stream. That's what also or what always the motto of value stream mapping is, learning to see and learning to understand your shop floor, your material flow. All right, so what we then can add here is also different kind of combinations. So I've described that we have here a process which is coming after inventory, and this process is receiving an incoming order. It could also be that you enhance this and you, for example, add additional object right here for processing, and in between you can add, for example, a FIFO element. So something, oops, like this. And then you connect this also to the customer. So this right now is not information flow control. So here would not be an information flow necessary or even allowed, because it's basically a material flow push. The process cannot decide what to produce or which product to choose if several are defined, and you would just move it through, and the material requirements planning algorithm is always jumping these, or is considering these, but it's jumping over these elements for calculation. So if a customer orders, then it's 60 parts, it will go upstream to the next station, and it will see, okay, this is the next control station, forward a certain order in here, take out parts from the inventory, and then calculate again to here, take out parts from the inventory. From here on, we would have a certain push system. Yeah, all right. And right here, yeah, just to change things, we would need to check the base product. So this right here is also the final product here as well. This could be something like a slightly smaller one. And besides product definitions, we could also do failures, or this similar tabs to plant simulation basic process objects, for example, with a failure or available percentage, technical availability during work time, and a mean time to repair. So how long is a certain failure rate? That might be more familiar with plant simulation users rather than lean users, but that's at least the way how failures are described the easiest in plant simulation with a process station. Yeah, and if you simulate this, you basically then have a push system right here, and due to failures and limited buffers right here, you will see, okay, inventory is piling up. You also have here quite a block percentage in the station. So the same experiment you would do with basic objects. Okay, test increase this capacity maybe just to gap certain failures, and to have again a balanced system there as well. Yeah, quite similar then to plant simulation there again, once it is in the push routine. All right. So 2 combinations. You have a push part within the system, and also information flow connection part where you forward elements. What I also can be done is to make, for example, the Gauss graph more interesting, is to integrate something like assembly station, where you can do something like this. For example, you add an assembly station right here, and then you would add connection right here. I'll just move the links in this. All right. So price question would be what's with this information flow. Since this is a FIFO and a process right here, that would need to be moved right here. So the order is coming in from the customer, is being calculated over this to this right here, and then it's internally distributed to the local order queue to take out parts from this inventory. And we can also define this to make this the parallel stream. So we could do something like this here as well, and have another supplier here as well. So we would connect these with material flow and also connect it with information flow. And right here, we wouldn't have a raw product, but we would have something different, maybe a subpart 2, which is then integrated and added to the assembly station right there. So we add the product definition with the subpart 2 hasn't been defined yet. Same packaging size. Yes, so the inventory, we have here a subpart 2 as well. And then we would have here the process assembly. So right here, we have a kind of different view because it's the only station which can combine two different base products. For the other station, it was always base product transition to main product. And right here, we would add assembled product. All right, and this is something like here. Okay. And then we would have here, one would be a raw product, and another one would be the second line from the bottom, which is here now, for example, a subpart 2. All right, so that would be added to this here as well. All right, and good. So here we have an assembled product, and then we need to transition here this as well. All right. So base product right here would come in as an assembled product and then going into a final product there as well. All right. So let us check this. Okay. And then the product would look like this. So we would have an assembled product, base part, raw product coming in. So it's more maybe of a complex product structure, not a complex, but you get a more structured Gauss-Syntrograph or product structure, which could then be extended further down the line. And yeah, if we then model this and run the simulation there as well, so the inventory right here would look the same. And what you can then add, for example, is processes here in the bottom. Once these processes are maybe too slow, you could change things up, that you say, okay, this line might be too slow for a certain assembly. This line might be too slow. You would see it also within part statistics, or if an assembly is waiting for certain parts, or if a certain process is waiting for elements. All right. Okay, just to show also quickly another concept of order control, or how parts can be controlled, is the introduction of a supermarket. So the supermarket would also be for the generalized purpose of storing, but it has more intelligence to it because it has to reorder parts specifically. There's also a logic behind it to replace object types with another type. So for example, here replace a simple stupid inventory with a supermarket with a reorder logic. So right here, for example, the subpart has now been taken. We can change a few parameters, for example, to 120 maximum stock and reorder level 60. So this is the additional logic, maybe, or for example, in comparison to the basic inventory. So it tells the supermarket, okay, once the stock reaches 60 or lower, it has to reorder 120, and the 120 are reordered also along the line of an information flow. So you define again a connection from supermarket to supplier, and then once the assembly takes out parts and you fall under the 60 mark of a reorder level, you reorder automatically so much parts that you reach the 120 target mark as a supermarket behavior and a simple integrated reordering mechanism with the supplier there as well. So you could then basically model this integrated in an integrated way, and also have the supermarket there available as a certain concept and push element, pull element for your value stream. This can now also be extended towards maybe a Kanban element, to have Kanban cards limited. You can also introduce a certain special order elements to give a sequence of orders coming into a station. You can also have transport externals, specific foreign orders, and to have additional workload on a station. But this would be kind of much to have to push this all into a short, maybe first introduction round for value stream mapping. And on this note or point, I'd also like to show you the third or the last agenda point of our meeting was how can we now push this to a very user-friendly interface to the shop floor, that users can also experience simulation even if they are not plant simulation experts. So to distribute this dynamic knowledge analysis behavior to users which might be lean users, which might not be plant simulation experts, maybe like most of today's session, but to have this in an easy, accessible way. And for that is the before mentioned add-on we've developed within first starting also with a research project, and then together with industry partners to more branches and to more industries, is a client architecture systematic where we have plant simulation as a calculation in the background. So basically you would use the logics you've seen right now as a calculator, as a dynamic calculator for your value streams, and you integrate this into a server. So you put an additional software to it and you let it communicate via TCP/IP and say, okay, and this is now available as a software as a service, as a simulation in the background. And to the front end, or as a connection to the server, you would have on the left side here a simplified overview or a graphical user interface, which also is implementing a toolbox for objects and icons mapped to the value stream library, and also mapped to a standardized set of icons there. And there you can also map your models in a location-based modeling interface, connect your objects there as well, put in parameter the same or quite similar to the plant simulation ones, and then by a click of a button you can transfer this automatically to plant simulation there as well. So just as a show or short preview of this, you would have the same or similar modeling environment where you can model certain elements, you can connect them with certain connectors, you have attributes, product assignments to your stations. Looks similar to plant simulation there as well. You have your toolbox on the left hand side, drag and drop elements, etc. And then by clicking a button, you would say, okay, run this on a server, which is now my local test environment, my local computer, build up a model, and then you can simulate the dynamics. This is automatically created, connected, automatically run. The results you've seen before also are automatically collected and sent back to a front end. And now a user on the shop floor on a tablet can look at its value stream and additionally look also at the utilization, for example, or the statistics we've seen earlier with the parts. Something like this. You can have part statistic here as well, or for example also choose other different alternatives. So you can make changes to structure or parameter within the subproject. So this project not only has one alternative, but maybe another and a third one. And you can compare static models within this project, so similar to an Excel file with different tabs, and then visualize your simulation results, and then also compare your simulation runs based on the results the simulation has given on a backend server. And then with different mechanisms, you would see, okay, for different stations, there's different utilization, or for example, for certain inventories, there's a different stock development and behavior depending on different strategies, parameters, etc. And that would be basically the integration or distribution of a simulation knowledge or accessibility of simulation knowledge to a tablet, to a shop floor, to an easy accessible environment as an add-on, which might be also helpful to distribute plant simulation and plant simulation as a maybe service to a broader audience compared to maybe plant simulation experts who use it 40 hours a week. All right, and with that, I think I've taken a little longer than 45 minutes, but we can come to the question part, or if you have questions to value stream, to the modeling, to information flow, or even to an add-on, feel free to ask or contact me later also as well. The contact information will be there as well.
Yeah, so if you came on late, the recording will be at the link that you see on your screen. You can click it now and bookmark that location. That is the Plant Simulation Virtual User Group inside our Siemens Software Community Forums. The other two links you see there are for our next two meetings. So Wednesday, March 11th is cost simulation is the topic. You can click there to register. Wednesday, March 25th. Worker batch processing is the topic. Click there to register. The other thing you see on your screen is the animation that's recommending that you follow the topic of the Plant Simulation Virtual User Group and then select to receive every post, because the only thing posted there are registration invites and recordings to these sessions. So just like this session, that will be posted there on Friday. So two more announcements and we'll jump in. For those of you who are able to stay, we'll also record this Q&A if you do have to drop. The team who runs Accelerator Academy for Siemens wants you to know there's comprehensive education there. There's a Plant Simulation Associate Certificate. Definitely click on that link if you're interested in learning more about that offering. And then lastly, Realize Live is our in-person annual event for Siemens software community users, managers, everybody. It's held in the United States, it's held in Europe, and it's held in India. Click on those links if you're interested in one of those locations.
Is there some documentation available for the libraries? So there is an integrated HAPE file within plant simulation. It's the old technology, so to speak, with CHM files. If you click on the objects there, there should be for every object on the top help, and then contents or help also an object, and then a CHM file should open up to have a more explanation on how processes are working, how parameters are used, an example, step-by-steps, for example, for a single station, for example. And can you show a realistic example before and after optimization use VSM? So yeah, so sorry, this was the plant VSM help file right here. if you go to an object, there should be help on object, and then there should be steps how a certain process is interpreted, how certain values are applied. All right. Can you show a realistic example before and after optimization using VSM? So a more complex example I might have to look up, but not a custom example. Just a second. So yeah. So more complex example could look like this, that you have also Kanban logic with supermarkets included, separate lines, certain different stations, assembly line, station line, yeah, to go through customer projects. I'm not sure if we have the time or even the the allowance to do that. Yeah, but I'm sure, yeah, this is a very simple first step value stream. This is not complex value stream we would build up over a one-day workshop.
Hi. Yes, thank you. I was just wondering for like, let's say like more complex assembly, so like even engines where you have relatively large bombs. So you have like up to like 20, 30, 40 different suppliers. How well does this handle that level of complexity and detail with parts incoming, especially when it's also talking about, you highlighted a little bit, parts incoming at different levels of the assembly?
Well, theoretically, it should handle also a bigger assembly list. So if you add several products, this should be fine. The question rather would be if you have 30, 40, 50 subparts to still have it quite easy manageable, then there would be maybe more need to go into detail of statistics. So which product is now exactly the slowest, or which product is now the limiting effect there, but there is no limit implemented to how much subpart assembly is working.
Okay. And have you done anything? Is there any like opportunity to connect into like ERP systems to pull? Because I mean, obviously, supply schedules can be very volatile and constantly changing.
Yeah, so in general, plant simulation has interfaces to draw data from a database or something like this. It just depends what data you might be using. So we often have discussions about cycle times or failure rates. Automatically drawing from a database, this normally is an issue of how you have aggregated your value streams, because value stream mapping is a manual mapping process. So you would define a certain station as one object with a failure rate and a cycle time, and maybe in data available providers, this might be 3 database lines, and then there's an aggregation issue could be. What also could be done is, for example, just retrieve orders. So if you would like to define a customer with certain order list, so to input a certain order list or a certain sequence of orders you might execute, that could be something which is more in a more integrated way. The issue is that a customer itself is locked, but that could be a mechanic maybe in the future we could add to say, okay, per method you can add some orders there. In general, plant simulation is able to handle this interface data. Typically, it's more the question of data aggregation to have this matching one-on-one with the value stream objects.
Okay. Thank you.
But this is, I think, might not be only a value stream mapping issue, but in general to make sure that the input data and the aggregation of input data is matching the level of hierarchy you have modeled in your simulation model. So, yeah.
Okay.
Yeah, thank you for this presentation.
Yeah, thank you for the invitation. Thank you for attending and the interest. And yeah, if you have further questions, you can also contact, so we'll be available there as well.
yeah, see you in the forums.
Yeah, thank you.
Bye.
Bye.